So today we're going to learn how to graph a new type of function that you saw in Algebra 1 but we have not yet studied in Algebra 2. Before I get started on the general form and the process of graphing, I want to look at a specific example. So the graph below is for the equation y equals 2 raised to the x power. And so we can kind of look at this graph and come up with some general observations. We should all be comfortable with noticing that our domain here goes from negative infinity for all the way from the left to positive infinity to the right. So our domain is negative infinity to positive infinity. Okay? And looking at our range, we're going to look at the y values. It seems as though, this is interesting, it seems as though the y values never cross the x-axis or the y equals 0 line. Okay, so it seems like all our y values are always positive. So I'm going to write that as our range 0 because it never crosses that line all the way up to infinity. And I'm going to put a little star here because we're going to come back to that at the end of this video. Okay, we can see that our y-intercept is 0, 1. Okay, so we can see that off the graph, but we also could plug into the equation. We could plug in x equals 0, so we could do y equals 2 raised to the 0, and we know that any number raised to the 0 power is 1. Okay, so our y-intercept is 0, 1. And then finally, notice, when is this function going up? Well, if we look at the general shape of the graph, this function is actually always going up. Right? So from negative infinity to infinity, it's always increasing, which means it's never decreasing. So now that we have these kind of general observations of this shape, let's look more at the general form of this function. So some of you might have already remembered that the function we're going to start studying are called exponential functions. And the general form for an exponential function is f of x equals ab raised to the x power. Okay, so a and b in this case are going to be constants. And x are up in our power, that's going to be our input. However, there's going to be a couple of rules about what possible values we can have for our constants. So we're going to call b the base, and we need to know that the base actually can never equal 1. Can never equal 1, and our base actually always has to be positive. So b can never equal 1, and b has to be greater than or equal to 0. Okay, we're going to look at two specific types of exponential functions. We're going to look at exponential growth, and this is going to happen when b is greater than 0, and it's going to have the general shape of a curve exponentially going upwards. Okay, and if you can think of this as our last example, 2 to the x, here our a value was 1, and our b value was 2, which was definitely greater than 0, and that's why it was increasing and going up. Exponential decay is going to happen, well, we know b has to be greater than 0, but I'm wondering what happens when b is between 0 and 1. When b is a fraction, what's that going to look like? Right? And we're actually going to get a general form of a function that is always decreasing and always going down, and you'll see some examples of this in class. So now I want to look at a specific example to graph. So let's look at the function f of x equals, my a value is going to be 4, my base is going to be 2 raised to the x power. We should already be thinking about what the general shape is going to look like. Well, my base is greater than 0, so I know that's a growth exponential function, so it's going to have a general shape of always increasing and going upwards. Now, just like many other functions from previous units, I want you guys to make a table when graphing. So I'm going to look at x and f of x, and let's first look at the points 0, 1, and 2. I'm leaving space above the 0 for a specific reason. Okay, so we know that when I plug in 0 for x, that's going to be my y-intercept. So I do 4 times 2 raised to the 0 power. I plug in 0. I know that anything raised to the 0 is 1, so that's 4 times 1, and I get 4. I find that really interesting that our y-intercept actually matches our a value. Okay, And before any shifts, which we're going to talk about tomorrow, that's actually always going to be true. Your y-intercept is going to happen at your 0, comma, a. Okay, so I know I have the point 0, comma, 4. All right, and then I can just start plugging in some other numbers to get the general shape of my function. F of 1, we do 4 times 2 raised to the first power, which is 4 times 2, and that gets me to 8. So I have 1, comma, 8. And then I'm going to have you guys trust me on this one, or you can double check my math, but I'm pretty sure when we plug in 2, you should get 16. But notice that's off of my scale right now, so sometimes you might have to scale these graphs yourself. But I'm not going to plot that because it's not on my scale. I want you to plot as many points as can fit on the scale. Okay? So I left the space above to look at what happens when I plug in negative numbers, because I know my domain is from negative infinity to infinity, so negative numbers should work. All right, so plugging in a negative number, let's look at f of negative 1, okay, and I do 4 times 2 raised to the negative first. And if you remember from the last unit with the negative exponents, that means this is 4 times, and the negative exponent brings my number down to the denominator. So it's like 4 times 1/2, or I get 2. So I have the point at negative 1, comma 2. Right? Let's look at f of negative 2. That's 4 times 2 raised to the negative 2 power, which is 4 times 1 over 2 squared is 4, and I get 1. Okay, so I have another point at negative 2, comma 1. Okay, and you notice, as my negatives, as I get more negative for my x values, I'm going to get smaller and smaller fractions. So my function's actually just going to continue to get smaller and smaller, but it's never going to go below 0. And this is actually the last part of the graph that I want to talk to you about, is what do we call this horizontal line that my function never crosses? If you remember that from the discussion of the range, and that's actually going to be your asymptote. So here I have an asymptote at y equals 0, and that's probably a new definition for some of you, but I guess to simplify what an asymptote means, it's just a line on the graph that your function never crosses. So here you can see that our function gets very, very, very close to 0 and kind of levels off at 0, but it never actually crosses it or touches 0. So that's going to be our horizontal asymptote, and it's going to be really important when we start to look at a little bit more complicated exponential functions and shifting them vertically and horizontally like we do with other functions. Well, be prepared to try to replicate this in class tomorrow and graph exponential functions. Have a good night.